upcoming sessions will be thank you very much. So the speaker of this session will be Joel Klassen, who will be talking about a compact fermion and qubit mapping.
Thanks, Kristen. Thanks for having me. Yes, my name is Joel, and I'm here today to talk about a new compact fermion to qubit mapping. Hold on, I'm just gonna change. Okay, good. This is something I'm quite excited about, and I hope you will be too. Oh, is there a way to hide the annotations? Okay, there we go. Oh my goodness. Okay. Before I begin, I just want to give a brief comment about the company that I work for. The company is called Phasecraft. It's a quantum software company. And the company's focus is on designing quantum algorithms that incorporate a detailed scientific understanding of all the moving parts of the algorithm design, from the particular application, say for instance, material simulation, to the specific hardware platform. And our main goal is to design viable applications for near-term quantum computers. We have partnerships with leading quantum hardware companies, as well as academic institutions and other industry leaders. And we're hiring full-time postdoctoral level researchers, as well as PhD level or earlier summer interns. So if you like what you see here at this talk, or you're interested in learning more, please check out our website and get in touch with us. You can also talk to me on Slack. So I should say, to begin, that this is joint work with my colleague, Charles Derby. He's a PhD student at UCL, as well as an employee of Phasecraft. And you can find our papers here at these two archive links. And I think I've put the links as well in the Slack. So let's start with the motivation. Why am I talking about this? Well, fermion to qubit mappings are important. And why are they important? Well, they tell us how to represent fermions on quantum computers. And there are many promising applications for the representation of fermions on quantum computers. For example, in material science and chemistry, right? The behavior of these systems involves the behavior of electrons, right? So we care about, which are fermions. Similarly, in atomic physics, the constituent parts of the atom are fermions. And in high energy physics, although I don't know a lot about high energy physics, I think I can say confidently that these little loop-de-loops are fermions, and there may be some application to quantum computers there. One important thing about these mappings from fermions to qubits is that they inform the algorithm design and the cost of your algorithm. So it's important to consider your options. So the punchline of the talk is that I'm going to introduce a new fermion to qubit mapping, which we call the compact encoding. And this compact encoding is a very resource efficient fermion to qubit mapping, and it can be tailored to various interaction lattices. And so the agenda for the talk is, first I'll give a brief overview of the fermion to qubit mappings. Then I'll give a general framework for a specific category of fermion to qubit mapping called local encodings, which the compact encoding is one of. Then I'll talk about the compact encoding and how it fits on the square lattice. And I'll explain how this can be seen as in its relationship to the toric code. And then I'll talk about some other nice lattices. And finally, if I have time, I'll talk about the cubic lattice and how we can put it on the cubic lattice. Just to begin, I want to get some notation out of the way. We're talking about Fock spaces, which we denote by capital F, on M modes, which we denote by lowercase m. The dimension of a Fock space is 2 to the m. We're going to deal with fermionic creation and annihilation operators denoted by these A's, and then Majorana operators. And there are two types of Majorana operators which act on the same site J. One, the first type, which can be denoted in this fashion, and the second type, which can be denoted in this fashion. And the thing to know about Majoranas is that they self-annihilate, i.e. they square to the identity, and they anti-commute with each other. Here, these curly brackets correspond to anti-commutation relations. Okay, so what's a fermion to qubit mapping? Well, a fermion to qubit mapping is a correspondence between fermionic states and qubit states. Or equivalently, you could say it's a correspondence between fermionic operators and qubit operators. A classic example of a fermion to qubit mapping is the Jordan-Wigner transform, which maps these fermionic creation and annihilation operators to long strings of Z's. And the Jordan-Wigner transform is a one-to-one mapping. It maps Fock states into computational basis states. And one feature of the Jordan-Wigner transform is that its operators grow with the size of the system. So as my system increases, you're going to get these long strings of Z's tracing through the system. And these higher weight interactions can be problematic because they lead to longer circuit depths. If I wanted to evolve under one of these long strings of Z's, if I want a unitary evolution, to one of these long strings of z's, then I need to decompose this unitary evolution into many 2-qubit gates. And so this means that the choice of your mapping can have significant consequences for the overheads of your algorithm. So why does the Jordan-Wigner transform have these long strings of z's? Well, it's because fermionic states have a kind of non-local structure, right? If you think about a fermion moving past an odd number of fermions, then you're going to pick up a minus sign in your state. Whereas if your fermion is moving past an even number of fermions, then you're not. And nature sort of gets around this kind of non-locality, right? It preserves the no signaling principle by parity superselection. You're not going to be able to measure this phase because observables in nature never mix the even and odd fermionic sectors. Okay, so what that means is that you're only going to get, you're only going to be in what's called the even fermionic algebra. And this even fermionic algebra consists of complex sums of even products of creation and annihilation operators, or equivalently even products of Majoranas. Okay. So I want to make some brief comments about the even fermionic algebra because I'm going to be using the features of it a lot throughout the rest of the talk. So you'll want to pay attention to this. Okay. The even fermionic algebra can be said to be generated by things called edge and vertex operators. And so the edge operators are sort of hopping of fermions of the first type, right? So there's a fermion of the first type at site J and a fermion of the first type at site K. The vertex operators are sort of switching the fermion type, so type 1 to type 2 on a single site. Okay, an example of how these edge and vertex operators can generate the even fermionic algebra is this hopping term, which is found commonly in something like the Fermi-Hubbard model. So you can say this hopping term looks like this. These edge and vertex operators are Hermitian, they're traceless, they're self-inverse, and they obey a kind of sign relation. Well, for the edges, if you swap the j and k, you pick up a minus sign. Furthermore, the edge and vertex operators anti-commute when they're incident on the same site, and similarly for the edge operators. So this edge operator and this vertex operator anti-commute because they're incident on the same site, and similarly for these two edge operators. One final condition that you should bear in mind, because it's very important, is that products of edges around a cycle must yield the identity, right? So this is sort of a loop gauge condition, okay? Okay, nature is local in the even fermionic algebra, and we don't like these long strings of z's. So let's try and do the same thing that nature does, right? Let's represent our fermionic interactions by choosing privileged elements of the even fermionic algebra and mapping them to local qubit operators. By local here, I mean they don't grow with the size of the system, okay? In these kinds of situations, when you try and do this, you're going to be mapping fermionic states into a stabilized code space. In this sense, the non-locality of your system is manifest in the entanglement of this code space instead of in the operators. Okay, two examples of local fermionic encodings include the Bravy-Kitaev superfast encoding and the Vertex ball encoding. And here you can see examples of edge operators. The privileged elements of the even fermionic algebra are the edges and vertices of these graphs, these square lattices. And the edge operator for the Bravy-Kitaev version looks like this weight 6 operator here. And it has a stabilizer, right? Like I said, these states are mapped into stabilized code spaces. And this stabilizer looks like this weight 6 operator here. Similarly, for the Vertex, you have a weight 4 edge operator. And you have a sort of a stabilizer that looks like a long Jordan-Wigner string, okay? So, what is the state of the art of these local fermionic encodings? Well, all of the known local fermionic encodings use at least 2 qubits per fermionic mode. Okay, so and many of them sort of butt up against this boundary. Furthermore, the best you can do in terms of edge operators is weight 4 edge operators, and this is in the Vertex encoding that I showed you earlier. And this is important because you use these edge operators to construct your Hamiltonian interactions. So any improvement on these numbers would reduce the cost of representing fermions on quantum computers. And the encoding that I'll show you today improves on these numbers by 25%. We use 1.5 qubits per mode. And the worst case edge operators in our encoding are weight 3. Okay. So before I go into the details of the compact encoding, I want to talk about a general recipe for constructing these local fermionic encodings. And all the encodings that we've looked at sort of can be put into this framework, even though they might say in their papers that they have a different design, protocol. You can sort of cram them all into this sort of mathematical construction. So let me explain. So we start with an undirected graph. And this graph sort of denotes the locality of the physical system that you're interested in, for instance, a square lattice. We take the sets of vertices and the directed edges of this graph. So we take the directed both directions of the edge, right? Which are these EJKs and EKJs. And we add some phases and we take the set. And then we impose all of the edge and vertex relations that I described earlier for the even fermionic algebra, except we ignore the cycle condition, okay? And this yields a finitely presented group, which I'm going to call MG, right? So this is the set of elements that form a free group, and then we impose these additional conditions from the even algebra, except the cycle conditions, okay? And now the cycles, the products of edges that form cycles in this group MG, form an abelian normal subgroup, okay? And then if you take this group MG and you take the quotient with the cycles, you effectively retrieve, as you might expect, the even fermionic algebra. More precisely, if you take the group algebra of this quotient group, then you get the even fermionic algebra. And you can associate, some of the edge operators with sort of these particular edge elements in the graph with coset with the cycle group. Okay. Okay, so why is this useful? Well, now what we're going to do is we're going to try and find a representation of the even fermionic algebra by first instead finding a representation of this group MG. Okay, so this representation sigma maps MG into qubit operators. Okay, and a good choice of this representation will map the edges and vertices in the graph to low weight operators. And now if our representation sigma of the cycle group happens to have a common +1 eigenspace, which we call U, then we may define a representation of this quotient group, right, by composing sigma with this projection into this eigenspace, right? And then this will give us representation tau of these cosets. Okay, so tau then will constitute a representation of the even fermionic algebra. And this representation will live in the code space stabilized by the representation of these cycles, okay? And the logical operators will be the representation of the remaining elements of MG. And this isn't new, but I think this particular formulation, it needs to be explicitly stated. And in particular, the difference between tau and sigma and the difference between, because fermionic systems, if you just look at the even fermionic algebra, there's no graph structure. And so we want to impose a graph structure so that we can say these are the privileged elements that we care about. Okay. So now let me explain how this works for our compact encoding. So here we're looking at a square lattice, just by way of example, and we're going to construct this representation sigma. Okay. And so what we do is we assign a qubit to every vertex, and we give every edge in the graph a carefully chosen orientation. And this orientation is a bookkeeping device, okay? So here we have odd and even faces. And sort of on the even faces, say, for instance, in this upper right-hand corner, we have the edges sort of cycling around the face. Similarly, in the lower left-hand corner, we have the edges cycling around in an opposite direction. And then on these odd faces, we sort of have the edges pointing into or away from each other on the corner vertices, okay? Oh, I'm making good time, so we'll have time for questions. So now what we do is we start with an ansatz for our vertex and edge operations. Okay, so we're going to say all our vertex operations are going to be mapped to Z operators on their associated qubits, and the edge operations are going to be mapped to products of X and Y operators. And in particular, the X operators are going to be on the tails of these arrows, and the Y operators are going to be on the heads. And then we also include this sign because there's a sign relation when we swap I and J. Okay. And now you'll see that by construction, all the edges are going to anti-commute with our vertex operators when they're incident, right? So for instance, here, all of these 4 edges anti-commute with the vertex operator. Furthermore, all the edges are going to anti-commute when they touch head to tail, right? So this arrow points to the tail of that arrow, and so then they anti-commute at that vertex, right? Okay, but you'll notice that there's a problem. And the problem is that when these incident edges are touching head to head or tail to tail, then they commute. Okay, so we need to resolve this problem, and the way we resolve it, so you can see here, right, these red parts here, there's four problems right there. So the way we resolve this problem is we introduce additional qubits, and we have our edge operators act on those additional qubits in a way which resolves the missing anti-commutation relations, right? Okay, so this edge and this edge act both on this qubit with an x and a y, so they anti-commute. It's also important to note that this edge and this other edge on the bottom side of the square both act with an x on this qubit, and so they commute. So we don't lose any of the existing commutation relations. And now you see why the choice of these orientations was very important as a bookkeeping device, because it allowed us to resolve 4 missing anti-commutation relations with only 1 additional ancillary qubit. Okay, and this, because you're adding fewer ancillary qubits, you're using few qubits per mode, so we only have 1.5 qubits per mode. And you're also making it so that because you're sort of localizing your missing anti-commutation relations, your edge operators are sort of able to resolve them more efficiently. And so our edge operators are able to be weight 3 instead of weight 4. Okay. Now, we said that we also have stabilizers, right? So what are the stabilizers? Well, there are 2 kinds of cycles that we need to consider, right? On a planar graph, all of the cycles on the graph are generated by the boundaries around faces. So we just need to look at the faces, and there are 2 kinds of faces. The first kind of face is the even face, where there is no qubit in the face. And on this face, we take the product of these 4 edges, and this is going to be in the bulk, right? So there's qubits around all of the sides. And we get this weight 8 edge operator, a weight 8 stabilizer, okay? So this is the only non-trivial stabilizer in the code, and I'll explain in a moment. And so this is around the even faces. And now on the odd faces, where there is a qubit on the face, we do the same thing. We take the product of our edges. And it turns out when you do this, you get minus the identity. And this is a problem, right? Because we demand that the representation of our cycles must have a common +1 eigenspace, okay? So how do we fix this? Well, it turns out you can fix this by just consistently flipping a sign convention on one of the edges around this square. And you can do this without interfering with any of the other ones. And so this problem can be resolved. Now this sort of cycle corresponds to the identity. That is to say, the cycle is in the kernel of the representation. And this is the only encoding that we know of, that we've checked, where the cycle space and the kernel space of the representation is not equal to 0 in their intersection, okay? Okay, so now what is the dimension of our code space, U? Well, we can take the log of the dimension of U, and then that's going to be equal to the number of qubits minus the stabilizer generators. And then the number of qubits is the modes plus the odd faces, and the stabilizer generators are the even faces. And so now we can define a thing called the disparity. And the disparity is the difference between the code space, U, and the fermionic Fock space, which is the thing we want to represent. Okay, and the dimension of the fermionic Fock space is the number of modes. So if we subtract those, then we just get that the disparity is equal to the number of odd faces minus the number of even faces. Okay, so that means that the code space dimension will depend on the shape of our lattice, right? So for instance, if we have the same number of odd faces as even faces, as in this case, then the disparity is 0 and we represent the whole Fock space. In the case where there are more even faces than odd faces, the disparity is -1, and that means that we represent half of the Fock space, either the even or the odd Fock space, depending on the sign conventions that you choose for the edges. If there are more odd faces than even faces, then the disparity is +1, which means that we're representing our Fock space plus some additional qubit degree of freedom, some logical qubit degree of freedom. So how do we make sense of this? Well, let's first consider the case when the disparity is equal to 0. In this case, the whole fermionic algebra must be represented, not just the even fermionic algebra, because we're representing the whole Fock space. This means that Majorana operators must admit a representation. So a Majorana operator of the first type anti-commutes with its incident edge operators and its incident vertex operators. Those are vertex operators in the same site. And so if we look at this lattice, we can see that at the corner, where the edges point away, they act with x's on that site, and the vertex operator acts with the z, which means we can identify a poly which satisfies the same anti-commutation relations as this Majorana, namely the y poly operator. And then we can sort of move this Majorana into the bulk by multiplying it by edge operators. right? So this means we can sort of inject Majoranas at these odd corners. There's another odd corner over here, and it turns out that if you look at the way the algebra works out between these things, you can identify the part. If you choose this corner to be sort of the canonical Majorana, then this other corner is going to correspond to a Majorana whole, where you have the Majorana multiplied by the parity operator. Okay. So now let's go to the case where the disparity is +1. Now there are 4 places to inject a Majorana operator, right? And so how should we make sense of this? Well, if we look at the way that these Majorana operators happen to anti-commute or commute, it turns out that the sensible way to identify these things is to choose one of the corner operators as the canonical Majorana. And then the other 3 are going to be whole operators tensored with some logical poly operator in this additional qubit degree of freedom. And you can see that if you sort of take 2 Majoranas from one of these whole corners and annihilate them at a site, then what you'll get is a long string of edge operators. And that long string of edge operators will correspond to one of these logical poly operators. So the poly operators on the extra qubit sort of are topologically protected, these logical poly operators. This logical qubit is topologically protected. And so for anyone who's been watching Naomi Nickerson's seminar or Ben Brown's talk, this might seem very reminiscent to you, and indeed you would be right. There's a surprise toric code hidden in this thing, okay? So if we zoom out and we take the stabilizers, right, the non-trivial stabilizers, and then we ignore the action of those stabilizers on the vertex qubits, that's these black dots here, what you get are toric code stabilizers, surface code stabilizers, essentially, up to some change in the poly, right? So here we have one around the plaquette operator, and here we have like the star operator over here, okay? And the paired magnetic and electric excitations of, so in the toric code, you can get magnetic and electric excitations corresponding to different syndromes of the toric code. And if you pair these magnetic and electric excitations up, then they begin to act like fermions, okay? And if you look at the way that an edge operator looks from this toric code picture, what you see are these paired magnetic and electric excitations. Namely, if I take a product of edge operators, which corresponds to the creation of a pair of Majoranas, then I ignore and I just look at like what the impact of that operation would be on the toric code stabilizers, right? Not the compact encoding stabilizers. Then what I would see is syndromes that look like paired electric and magnetic particles there. So there's a sense in which this code is pulling these paired electric magnetic particles into the code space. And this is not entirely new. The stratospheric encoding also talks about some relation to the toric code. And so this is kind of unsurprising, but this is quite nice and clear in our construction. So our construction is very versatile. It can be applied to many different lattices. So here are a few of them. We have the hexagonal lattice. We have the 6-4-3-4 lattice, which is one of my favorites. We have this 12-4-6 lattice. And all of these lattices, by way of, have zero disparity in the bulk. So as I grow the size of these systems, the only difference from the code space to the Fock space is going to be determined by the boundary conditions, same in the square lattice encoding, okay? We could also put this thing on the Kagome lattice, and if we're really keen to have our edges be weight 3, we can do it, but then something interesting happens. As we grow the size of our system, the disparity increases. And so, Oh, okay. And so the disparity increases, and so we can do something similar to what we did in the square lattice encoding. We can identify where there are injection points for these Majoranas, and we can annihilate them and create stabilizers, which can project out these additional logical polys. So we explain how to do that in our paper. One more thing for 2D lattices before I go to 3D is that there's one very nice lattice that I want to draw your attention to, which is the 488 regular tiling, which we can do here. It's very similar to the square lattice encoding. And this can be used to represent spinful fermions on a square lattice. So you can take these pairs of qubits or pairs of modes around this octagon and treat them as the different spin configurations of a fermion. And then you can get sort of spin hopping terms that are weight 4. And the encoding would use 1.25 qubits per mode. And the whole thing can be put very naturally on a planar hardware layout. So we think this is quite promising for something maybe like spinful Fermi hybrid or something like this. Okay, one last thing. We can put take the 2D encoding and we can extend it out into 3D. Okay, so what I have here is an illustration of this. Every slice of this 3D cube looks exactly the same as our 2D encoding. Okay, and you can kind of see that. And the edge operators are weight 4, and the encoding uses 2.5 qubits per mode. And this is in contrast to, for instance, the Vertex encoding, which uses 3 qubits per mode and also has weight 4 edge operators. We can compute the ground space disparity by looking at the number of sort of odd corners, which are these corners which are adjacent to 3 odd faces. And the disparity is equal to the number of odd corners divided by 2 minus 1. Okay. And this is a non-trivial fact. It requires a bit more thought because the kernel of the representation is more complicated and the cycle space is more complicated. Okay, so some open questions. Is our construction the best one can do by these metrics, as in, you know, weight of edge operator and qubit number, right? Can we do better? I mean, I don't think we can, but you know, we could try. Am I running out of time here? Can we transition gradually to questions? Yeah, maybe. I mean, I can keep these questions on the board, and if I can open up to questions now, if that works better. Hello.
Okay, thank you very much. There's a couple of questions in the chat. So, for instance, Angelo Lucia wanted to know whether you looked into actually using higher qubits on every vertex to represent the fermions, whether this gives something better to represent the fermion algebra?
Yeah, I mean, our motivation for this work is largely about bringing down resource costs in actual real applications. And so, you know, our primary interest has been in qubits because those are the things that people are typically making. So we haven't really given that a lot of thought, no.
And have you looked, and another question that was asked beforehand, just have you looked at different graphs that are sort of non-planar or something? So if you look at chemistry problems, would encoding like that work for chemistry problems as well?
Yeah, in principle, there's no reason why the design principles applied in this encoding can't be applied to other graphs. I mean, a good example is this cubic lattice, right? This is non-planar, but indeed you can sort of just start constructing graphs and putting arrows where you like, and then you just have to find the right places to add additional ancillary qubits to resolve the anti-commutation relations. And you know, the design principle at play here is to say, you know, bring your anti-commutation relations that are missing close together so you can resolve more of them at once with fewer qubits. This is sort of the premise here, and that's what we're doing in sort of an optimal way for this square lattice, I think.
Thanks. And there's another question. So Tyler Ellison wanted to know is whether you could comment on how your encoding compares to the encoding by Chen, Kapustin, and Redichevich. Do you know that encoding?
I'm sorry, I'm not very good with names. We have a table in our paper. You're welcome to go take a look at it. If we've missed something, please get in touch with us. But I feel like we've been pretty comprehensive. So I think ours is still better, probably, but I don't know.
Okay, I think the paper, just for reference, was called Exact Bosonization in 2 spatial dimensions in a new class of lattice gauge theories.
Oh yeah, I think I have read this paper, and I think we looked at this closely, and we came to the conclusion that we think it's not too dissimilar, if not exactly the same as the Bravik-Kitaev superfast encoding. But I don't want to start throwing around flack or anything like this, so take that with a grain of salt. So I think if you want to make a comparison, think about the Bravik-Kitaev superfast encoding. That would be my best guess.
I see. Okay, then I think that's pretty much it. We're in. So I would thank you very much for the very, very nice talk. That was a really, really nice talk.